All right, so in this section, we're going to be talking about GI, or Global Illumination. We can get to our GI options in the render settings. If we look at the Redshift render tab and click on GI, you'll see we have a whole good old tab here. We're going to take a look at all this junk and figure out what it does. So the whole purpose of GI is to give us our bounce lighting. You can see by default, in this scene, we have no bounce lighting. And let's think about what that really means. So just going to zoom out of my camera here for a second. Give us a little more space. So in this scene, I have a giant light over here on the left. And we would expect that this side of our spheres wouldn't be just black because they've got all of this bright area around them. We'd expect to see, some extra color here on the right hand side of these spheres from just, light bouncing around off of the floor and the walls, etc. And that's where GI comes into play, because without GI, all we have are rays firing from our camera, hitting objects in the scene, and trying to find lights. Now, to be clear, GI really only has a major effect on diffuse surfaces. In fact, the calculation is only actually done on diffuse surfaces, but it will affect other types of rays that are being traced, like reflections or refractions, etc. But in almost all cases, GI does not consider those aspects of the material and is only calculating based off of the diffuse surface values. The one scenario where it may have a great effect, actually, would be in the case of reflections, light reflecting off of something and illuminating a surface, or if you have a glassy material and a bright light shining through it, you would see it reflected out of, or rather refracted out of, the glassy surface and onto surrounding surfaces. And we're going to go over that effect in the caustics section, so go ahead and take a trip on over there if that's what you're looking for. So, like I said before, right now, all we have in our scene is, in terms of ray tracing, are rays being fired from the camera into the scene, hitting objects and looking for lights. In this scene, we find the light off on the left, and that's what creates our shadowing on the right-hand sides here, as well as these wide, soft shadows on the background. And we'd like to see a little bit more light interaction than just that. So we'll go ahead and head over to our good old buddy GI, and to start with, let's just see brute force approach and what that looks like. So now you can see immediately when I flip this on, the other side of our spheres light up in a way that our brains are familiar with seeing. We get some blue bounce onto our left sphere, as well the right sides of our spheres are completely lit up, and we've gained some additional brightness off on our background from light from the walls bouncing onto each other. Now, one of the first things we'll notice when we're looking at the GI tab is that we have a primary GI engine and a secondary GI engine. That might sound a little confusing, like why do I need two? Well, it turns out that by leaving our options open in terms of how our GI gets traced, we gain particular advantages by combining different methods between our primary and secondary GI engines. And we'll go over that in just a minute. I think the main thing to understand here is the difference between what primary GI and secondary GI means. So let's start with none again. Now let's just quickly recap that we only have rays firing from our camera, hitting the surfaces, and looking for lights. Well, in order to get all of that bounce lighting, we actually need to add some more steps in there. And the way we do that is by adding more rays or ray bounces. So if we flip on our primary GI engine to brute force, effectively, what we're doing is we're saying, okay, now we're firing a ray into the scene. We're going to look for lights, and then it's also going to fire a second ray to go gather light information from the other surfaces in the scene. And we're going to call that our first bounce of GI. Now, from that point, we can then take additional samples or fire additional rays to do bounces beyond that, because to get more realistic results, we need more than just one bounce. And that's where our secondary GI engine comes into play. In this case, I'm going to flip on brute force just for this quick demonstration. So now what's going on is we have a ray being fired from the camera. It hits our surfaces, it looks for lights to get our initial direct lighting. Then it fires rays from that point to look up the lighting on other parts of the scene. But instead of doing that just one time, we're going to allow it to bounce up to 3 times, which means our results should look a bit more realistic. Now, I know you're probably thinking, well, that's a nice explanation, but I'm really kind of having trouble visualizing that. So I've actually gone ahead and made a visualization for what's going on in good old Houdini. Don't worry about any of this other crap. We're just going to look at our scene here. So right now, we're just looking at one camera array, and that is the red line in the scene. In just a second, I'll add more, but right now, let's just look at one ray. So we fire our camera array, and we find our sphere here. And we say, okay, cool. Let's see if we find a light. So let's fire another ray to look for lights. And we found a light. So that means we're going to color this point on our surface as though it were lit by this light. Conversely, if we were looking at the dark side of our orb, we would not see the light, so we return a value that says we didn't find a light. And it's at this point that we will send our first GI rays. Now, GI rays and light rays aren't the only rays that get sent. There are also refraction and reflection, volume rays, etc. But in this case, we're just looking at light rays that are represented by this yellow line, red rays, which represent our camera rays, and then we're going to also add this teal and green ray as color as well to represent our first GI bounce or primary GI engine, and as well as a second bounce. And we're only going to go up to second bounce because it's probably going to get a little complicated to look at after that. So we fire our ray from our camera. We check to see if we find any lights, and then we're going to send our first bounce of GI. Now in this case, I've found the blue sphere. So we're going to say, cool, found blue. This surface should have a little bit of blue on it. Then from there, we would send more rays, or more bounces rather. And in this particular case, it just fires out off into the sky. So we would have no additional light contribution onto our initial point that we were tracing for. So in this case, the primary GI engine would be responsible for finding the result of the teal ray, and our secondary GI engine would be responsible for finding the result of the green ray. Now, let's run that one more time, just this time with an image plane. So we'll just go ahead and flip on our image plane. And we're going to keep our image plane rather low resolution. Maybe let's try like a 6 and a 8. There we go. So we've got that same principle happening. It's just that instead of one ray or one pixel, we're now firing many rays, each one representing a pixel. So we have our initial camera rays, which you can see find the intersections of our objects. And then we're going to go ahead and trace for or send rays to find lights so that we can do our initial direct lighting shading. So we found lights on these points, and we know the brightness values for them. So now we can go ahead and send our first bounce of GI. And we can already see it's looking kind of complicated, but I think it helps illustrate the point. And then from here, we would go and find our second bounce. Now in this example, we're actually only looking at one ray being fired per bounce, but in reality, what's actually going to happen if we switch back to our single ray is that we're actually going to get a lot of bounces for just our one camera array. Let me go ahead and trace this back. So again, we're firing our primary camera array. Then more realistically, we'll likely have a handful of samples being sent per camera array. So you can see we find some samples that are finding the floor down here. We see some samples that are finding our bright wall on the right. We can see some samples that are finding our blue sphere. And these are all going to contribute to the value that we determine for what colors of light should be found for our global illumination on this particular point. Then, of course, we add our secondary GI engine and start looking for additional light contribution. And this ultimately represents a little more closely what our camera ray actually might look like. Totally not an educational moment, but I think it's super fun changing what the primary ray finds and watching all the other junk update. And now we're hitting the back wall there. Anyway, it's a pretty interesting visualization, I think. Okay, moving back to C4D. So brute force is precisely like the example that we just showed. Now, a downside to brute force is that generally it will require a ton of samples to clear up in certain scenarios, namely scenarios where there are big flat surfaces involved. Dual brute force approach can be a bit slow to calculate, especially when we have other approaches that can, clean areas like this up very quickly. So let's flip off our secondary GI engine for a second. You can see we get quite a bit darker because we're only firing one ray out, one bounce out for our GI lookup. Let's take a look at another option, which is a generally faster to calculate but a bit less accurate GI engine, and that is the irradiance cache. So flipping on irradiance cache, my settings are pretty low, but this will kind of illustrate some of the issues you may run into with the irradiance cache, and that is that you get these splotchy, or can get these splotchy looking areas in your GI calculation. And we'll go ahead and show you how to avoid that. It's actually kind of a neat process. What ends up happening is Redshift will fire, or rather scatter, a bunch of points into your scene from the camera's angle, and scatter points across the surfaces visible to the camera, and then only from those points will it fire the GI rays. So you're actually firing a significantly fewer number of GI rays with the irradiance point cache, which is actually quite cool. So if we look under the irradiance caching dropdown, you'll see this visualize points option. And if I tick visualize points, instead of displaying the GI, it's actually going to show me the points that it's using, or rather the points that it's scattered to figure out the GI. So if I zoom in on this guy, we can actually see the points the Redshift has figured out that it needs to scatter and then fire rays from in order to gather our GI based off of all of these input arguments that we have under the irradiance caching tab. We can also see a rough representation of the color values that it's found. If we take a look around, we'll probably see the variations in points that we were seeing in those splotchy effects. We can kind of make out here where some of those trouble areas might be. So let's go ahead and take a look at what all of these options mean. So min rate and max rate basically define a scale on your image at which Redshift will iterate through scattering the points. Now the scale is based on image resolution. So if we start with a min rate of -2, we start scattering points on an image that is 2 times smaller than our original image, and then it will iterate through up to whatever our max rate is. Right now I have that set to 1, so that actually means it will start with an image 2 times smaller than my current image. Then it will iterate through -1, which is 1/2 of the size of my image. Then it'll iterate on the image resolution itself. And then since I've set max rate to 1, it's actually going to also iterate through a resolution that is 2 times my image size. So I'm actually going to go ahead and set this back down to 1. And you can see, or 0, you can see if I set my min rate down to, let's say, -5, my points become very, very sparse. And there are much less of them. And as I start to walk this up, let's say take this to -3, you'll see progressively it looks like we're getting more points, and they're also separated a little more evenly. Now, color threshold is a pretty interesting one, actually. This is essentially a bias towards points of the scene that have higher contrast in color. So with a lower color threshold, Redshift is going to pay more attention and feed more points into the areas in your image that have a higher contrast in them. Distance threshold also is a bit of a bias toward objects that are near each other. So for example, if we take a look in this corner, we'll see we've scattered higher density in the corner than we have out in this sparse wall back here. And that's because we have our distance threshold set to medium. You'll see if I set it to very low, what was a very dense scattering along our corner here is now going to be quite sparse by comparison. So distance threshold is a bias toward objects that are near each other. So we'll go ahead and leave that guy at medium. Normal threshold is also a bias, and this essentially has to do with the curvature of a surface. So where the more curved a surface is, the more points it will scatter on it. So for example, if I flip this guy to high, we're going to see many more points on our sphere, whereas our background, which is not very curved at all, does not receive any additional points. So flip that guy back to medium as well. All right, so min detail is kind of an interesting one. Essentially, it's saying try not to put any more points in if it would mean being closer than min detail distance apart, and the distance for min detail is in pixels. So right now I've got it set to 0, and if we crank this guy all the way up to 8, we should see that our points that would otherwise be within 8 pixels apart from each other are no longer there. Now, as you start to increase other biases that add more points in, min detail is going to be less and less effective. For example, if I take min rate and set it to -1, we're going to see lots of points return, even though they are within 8 pixels from each other. You can see if I flip this down to 0, this will look pretty much the same, with the exception of our corner, which we've gained our points back from our distance threshold set to medium. All right, so moving along to radius factor. Now this has an effect on the final pixels, so we're actually going to want to flip out of our visualize point mode for a second. Radius factor is going to help tell Redshift how widely to sample points that are next to each other when calculating the final pixel. So it's kind of almost like a smoothing. Wouldn't really necessarily recommend using this for a final render, but it could certainly help you speed up previs renders or something like that. So you can see now that our splotchiness is smoothed out quite a bit without looking like it's gotten too blurry. And that's essentially what radius factor is for. Now we move on to num rays. This is the bulk of the heavy lifting. So each point that we were looking at before that gets scattered into the scene is ultimately used as a point to fire rays from. And num rays is essentially the number of rays that will get fired from each one of those points. 15 is super low. I definitely would not recommend using that. Let's set this guy up to 200 and see if that evens out some of our splotchiness that we've got going on here. So there we go. Most of that splotchiness that we saw is now gone because we've simply sampled those points with way more rays. So it wouldn't be a Redshift feature if it didn't have some adaptive quality to it. So underneath num rays, we have this adaptive amount. And this is basically a percentage of these num rays that we're going to fire. So if we're set to 0.8, for example, that means 80% of the 200 rays, so 160 of the rays, are up for grabs, meaning we may not use those. We're basically saying definitely fire 20% of the rays, and then based off of our adaptive error threshold, decide whether or not to fire the other 160 rays. And lastly, we have num smoothing passes, and this will work similarly to radius factor, except that it's actually just straight up going to blur the values of the irradiance cache points together. You're going to lose significant detail, so again, I would not use this on final render. But in the case where you're just doing, previs renders or look dev, maybe you might be able to just smooth those points out if it's giving you trouble. And that about does it for the irradiance cache options. Just quickly before we jump into secondary GI options, just want to briefly go over the photon map approach. This is kind of an old school approach where you fire photons from the lights rather than using camera rays to discover what surfaces you need to find the shading for. It is widely not used very much at all, ever. And I would definitely bias you toward brute force or irradiance cache approaches. Okay, so on to secondary GI engine. I'm just going to go ahead and flip brute force on as the primary GI engine. So secondary GI is going to come into play if we want to see more than just an initial bounce of GI. I would say in many cases you're going to want a secondary engine. If I just flip brute force on, you'll see the difference between the current scene that we're looking at versus now we're rendering with a secondary GI. You can see we've got quite a bit of blue spill on the floor here. Our entire right side of our wall has a lot more light as well. That blue is bouncing a lot more noticeably and nicely onto our second sphere here. And brute force is very straightforward. You just flip brute force on, and the brute force GI rays contribute to both the primary and secondary GI engine. And that's really all there is to it. We do have a couple other options. Of course, we have photon map, which again I personally consider as deprecated and never use. But we also have irradiance point cloud. And this one's actually quite good for scenarios where you want to use a brute force primary GI and you're just having trouble cleaning up the GI without using an absurd number of brute force GI rays. You might want to take a look at the irradiance point cloud option. So irradiance point cloud goes under the assumption that we only need a coarse or very grainy solution for our additional bounces of GI, as they won't introduce any artifacts to our primary GI engine. So essentially what irradiance point cloud does is scatters a bunch of points on the surfaces, similar to photon mapping in that way. As well, irradiance point cloud will cache points that are on occluded sides or sides that are not facing the camera, because they'll likely be needed for additional bounces. So if I just flip this guy on again, you'll actually get to see the very rough secondary GI engine compute when set to irradiance point cloud. We'll see we get this very grainy solution, which ends up being actually totally fine because it is not our primary GI engine where most of the heavy lifting is being done. So let's go ahead and flip down the irradiance point cloud options, and you'll see there really aren't too many. We have the show calculation option, which allows us to see that cache happen. Again, it's that very grainy solve that you just saw there initially. Screen radius actually refers to the number of points in screen space that we're going to end up using for the final calculation. The higher the number, the more points we're going to end up storing for the scene, and therefore the better your secondary GI results will look with the irradiance point cloud method. And samples per pixel basically determines how many samples we're going to fire, initially determining that point cloud. So if I double this guy up to 32, for example, you'll see that my calculation time is going to be a bit longer, but it's also going to get a bit less grainy. So essentially what's happening is we have that calculation phase that happens, and then we store values in points that have been scattered around the scene based off of what that initial calculation finds. Samples per pixel simply increases the quality of that initial calculation. Now filter size has to do with the interaction with the primary GI engine. So once we go to calculate our primary GI, which in this case will actually happen after the irradiance point cloud is calculated and stored, when our primary GI engine rays go to find the surface values to report, they actually go and look for the irradiance point cloud points that we've stored around the scene. Filter size simply controls how many of the closest points to that primary GI engine ray will end up getting used in the calculations. So if you end up increasing your filter size, it will blur out that result a bit. And actually, if you find that you're increasing your filter size, you might want to consider just upping the samples per pixel first, as that's a faster way to calculate a more even distribution than simply increasing filter size. And retrace threshold is actually kind of an interesting one. So because we have no way to weight toward curvature over the surface or towards objects that are close to each other, for example, like a corner, we end up kind of getting this even distribution of points across the screen, which means that we're not actually going to be recording a ton of detail for something like this corner. And this can actually lead to some problems. And retrace threshold basically just biases away from using the points that get sampled along these areas. The higher the threshold, the more it's going to bias away from using the points near edges like this. Now, in terms of case uses for the different GI engines. I tend to try to use brute force as often as I can. However, when I run into grain issues across large surfaces, then I'll start to tend to bias towards a radiance point cloud as the secondary GI engine. And if it's still an issue, then I will attempt a radiance cache as the primary GI engine. One drawback to a radiance cache is that it can use quite a bit of memory the higher your image resolution is, because you need to store more points. So that's something to keep in mind when picking which GI engine to use in your particular case. But there's also something comforting about knowing that dual brute force will work, sometimes as a matter of render time. Anyway, I hope you enjoyed this section. If you want to know more about photon mapping, we'll actually go over caustics, which is a photon mapping type, in the caustics section. So go ahead and take a look. Anyway, thanks for watching this section, and we'll see you in the next one.